Today we'll do an example of the direct comparison test. Okay, suppose we have the sum n equals 1 to infinity of 5 over 2n squared plus 4n plus 3. Now, we cannot directly solve this problem, but we know that this is similar, so we can compare it with. This looks similar to something like, if we just ignore the lower terms, this is about the same as 5 halves n squared. Well, you can pull out a 5 halves outside, and this is a special series. Would you agree? This is just a p-series test. Ooh, there's a typo here really quick. Let me fix that. 5 over 2n squared. 1 over n squared. And what do we know about 1 over n squared? Well, that's a p-series. Your p is 2 greater than 1. And this is, if something converges and multiplied by a finite number, it still converges. Therefore, this series converges by the p-series test. So now we can do a comparison test, and for this case I'm going to use direct comparison. And recall the image that I always use. So what are we trying to say? We know this converges, and so the only way we can use the comparison theorem is if we say if the bigger one converges, then the smaller one has to converge, right? So we have to show, or need to show, that 5 over 2n squared is greater than 5 over 2n squared plus 4n plus 3. For now, I'll just put a question mark. And one easy trick to do this is, you note that the numerators here are just constants. So I can just actually look at the denominators first. One thing we know is, if we just compare the denominators, is that 2n squared we know is actually less than 2n squared plus 4n plus 3, because we are always dealing with positive n, specifically n greater than 1. Well, if everything is positive and things are fine, then we can flip it over and the signs change. So 1 over n squared is greater than 1 over 2n squared plus 4n plus 3 for n greater than 1. And now, if we just multiply the same constants to both sides, the signs will not change. Therefore, 5n squared, 5 over 2n squared is greater than 5 over 2n squared plus 4n plus 3. And so therefore we can conclude, since we have shown that 5 over 2n squared is greater than 5 over 2n squared plus 4n plus 3, and we know that the sum of 5 over 2n squared converges by the p-series test, which we showed about, we can say that the sum of n equals 1 to infinity of 5 over 2n squared plus 4n plus 3 also converges by the direct comparison test. And that will be all from